In the previous design, we did a 2-to-1 multiplexer using gate level design. And what that means is we instantiate each of the gates within that design independently. We instantiate them like this, and then we connect them together using the internal wires. And this worked. We verified this on the DE0 Nano board for a 2-to-1 multiplexer, and we saw that this worked. Now, this is all well and good for a very simple design like a 2-to-1 multiplexer, but we want more complicated designs with what will be many, many more logic gates, and it becomes not practical to do this at the gate level. And this is why in Verilog, behavioral programming style was introduced, in which we can describe the behavior of the design rather than the gates themselves. So there's a higher level of abstraction, and this makes it very powerful because we don't have to worry about, instantiating and arranging these logic gates. We actually leave that to the compiler. And this is what makes hardware description languages very powerful, because we only care about the function of the design. We don't care about the particular arrangements of all those logic gates within the design, how they're connected together. That's a job that can be left and automated by the compiler. So what we're going to look at today is the behavioral way of doing this design. So functionally, it's going to be the same, except we now use essentially an if statement to do the same thing. So what I'm going to do is I'm going to go to File, New, Verilog HDL file, and I'm going to start a new module, and I'm going to call it multiplexer behavioral. By the way, the name of the module doesn't matter. You can call it whatever you want, but it's always better to use a descriptive name so you know exactly what that module is. I'm going to have the same port list as the other module, which is A, B, select, and then the output. I can save a bit of time by copying and pasting the input and output declarations from the other module. Now, we're going to make a change to this output a bit later, so keep an eye out for that. But what we're going to do now is we're going to have an always block. So always at. Now, in Verilog, these always blocks are incredibly important. And what it means is if you have an always block, whatever's within those brackets, that's the sensitivity list, and the code within that block will execute whenever anything changes within that sensitivity list. So if we actually put A or B or select, whatever's inside this block should execute whenever A changes, B changes, or select changes. And that's exactly what happened if you think about it with the other design, because in a combinational circuit with just logic gates, the output will change and update whenever any of the inputs change. It's not waiting for anything else. Later on, we will look at always at positive edge of clock always blocks, where it actually waits for the positive edge of the clock before the update happens. And that's called synchronous logic, and that's something we will have to come to a bit later. For now, let's stick with combinational logic using logic gates, because this is the easier to understand. Now let's do an if statement, and what we can say now is if A, so if the what we can say is if select is equal to 1, or we can just say if select. That's the same as saying, select is equal to 1. Then what we can do is we can say out1 is equal to A. That's exactly what we had in the other design, because if select was 1, then the output took on the value of A. There's only one other possibility, and that's if select is 0, in which case out1 is going to take on the value of B. So that's all we need to do. So that's the always block. Now you have to be careful with the begins and ends, so every begin must have an end. If you have an if statement like this, if there's only one term within the if statement, you can get away without having begins and ends within the if statement like this. So that's our if statement, and that's our behavioral multiplexer. So I'm going to save this, and I'm going to call it the same as the module name, behavioral, multiplexer behavioral. So I'm going to right click and I'm going to create symbol file for current file. It's going to check the code, and we have a mistake. So let's see what the mistake is. Now this is what I talked about earlier about the data type of out1. Now whenever you use always blocks, the thing on the left hand side of the assignment must be a register. Now a register is it's a different data type in Verilog. So you've either got wires, which is basically what we've used up to this point, or you have registers. Now they're the only two data types essentially that you can have in Verilog, or that they will cover 99% of the cases you'll come across. So we're going to talk more about the register data type a bit later in the context of behavioral, in the context of synchronous logic, because it has a very special meaning in that respect. So, but at the moment, just accept that we need the register data type on the left hand side of an assignment in an always block. So let's save, and let's try to create that symbol again. So that's successful. So what we can do now is double click and drop our new design, delete the old one as the block, plug that one in, same procedure, compilation. Okay, now typically if you don't need to change any of the pins, you can just go straight to compilation. If you need to change any of the pins or anything within the block diagram schematic file, you have to do analysis and elaboration and then compilation. Right, so that's successful. So let's go to Tools, Programmer, and let me just check output files. It's always worth checking. Just check the date that the new SOF file was created, just to make sure that's the most recent one. I can see that is the most recent .sof file. So let's send the .sof file to the board. So you can see it's failed. If it fails, just try again. And now it's successful. So there we go. So we have our multiplexer. Now, if I remember correctly, it's a 2-to-1 multiplexer. This is the select pin. At the moment, both A and B are in the same position, so it doesn't really matter what the select pin is, you're going to get the same output. Let's change A and B so they're different. Now, if the select pin changes, the output will change because A is 1 and B is 0, so that will change depending on the select pin. So there we go. That's a 2-to-1 multiplexer using behavioral Verilog. And again, this is much more powerful than doing things at the gate level. And the reason it's more powerful is because when we start doing more sophisticated designs, you cannot do them at the gate level. You have to describe the function of the design, not the actual gates within the design. Now, it's important to say that the compiler will actually produce the same. So the compiler will look at your code, it will do the compilation, and the actual design that gets sent to the board will actually be the same as the gate level design. So there's no compromise here, but it's much easier for a human to write things as, in terms of if statements, rather than at the gate level. That doesn't really make any sense, especially as the design becomes more complex. Okay, so that's behavioral design with the multiplexer using the if statement.